welcome to the Reproducibility Workshop for the TIES 2023 conference. And we're going to talk about how to integrate reproducibility into Rstudio and how to use something like GitHub to track your changes for your code and your projects and so on. All of the material for this workshop are available at this URL, which is a permanent link. And in fact, it's all linked GitHub, which you'll see a little bit more of as we go through this workshop. And actually there's a repository where all of the source files for the slides, the information on what to do before the workshop, and the actual little website you were looking at is all contained. And you can go and grab that anytime you want. And this is for July 24th. So some definitions to get us started. Reproducible analysis, the idea is to reach the same result given the same input. We're going to formally define that from the scientific literature in a moment. We're assuming that you are familiar with R and have used R before, and that you want to get better at it, that you want to do things in a more proper way. So let's get started. If you click on this link here, it will take you to bit.ly/TIES2023_reproducibility, which leads us to this set of slides. And we're going to get going. Actually, sorry, it doesn't. It leads us to this set of slides with this amazing quote. And so this is from Mark Holder, and he says, "Look, you mostly collaborate with yourself, and me from 2 months ago never responds to email." This is actually true. The person who edits and works most closely with your work is yourself. But you from the past. And you from the past is a jerk. You really don't like documenting things. You don't like writing things down. And you from the future really wishes you from the past were better. So we have 4 slide decks we're going to work through in this workshop. This video will cover slide decks 1, 2, and the start of 3. And the second video after the break will cover the rest of 3 and 4. Let's get started by defining reproducibility. We are specifically interested in this workshop in discussing the ways to encourage students, professionals, faculty, people who work with science and data and code to develop the skills and habits for strong, reproducible research methods, particularly with respect to your data gathering, your data manipulation, and your data analysis. Now, the first published work that I've been able to find in the literature that discusses the specific framework, this idea of computational reproducibility, is from 1992 and came from work that ran from 90 to 92 by Jay Clairbeau at Stanford. And it is an AGM, sorry, it's an AGU thing. So annual international meeting of the Society of Exploration Geophysics, which is part of the AGU, and it is in the proceedings. And it is a very short little thing. It's all of 1.5 pages long. And the title of it is Electronic Documents Give Reproducible Research. Oh, excuse me, a new meaning. Let's look at some quotes from it. "A revolution in education and technology transfer follows from the marriage of word processing and software command scripts." Okay, so cast your mind back. You may not be old enough to remember 1992. I am. I was in primary school in 1992, but that meant I was using computers in 1992. So that meant, like, by the time you get to 1992, you had a desktop computer, a personal computer, a PC on the desk of many faculty in many research institutions. And that meant that we were transitioning from the era of mainframe computing and of typewriters to all documents being electronic. Researchers can reproduce their own research results a year or more later by, quote unquote, pressing a single button. And our basic goal is reproducible research. The electronic document is our means to this end. And so there's a DOI there, and you can go check it out, actually, because I'm sitting in a browser right now. Let's do it. Let's go take a look. We click on this, and as you can see, it comes up, and it's all of 2 columns. And it's just some comments on reproducible research as part of this 1992 Society of Exploration Geophysics conference. Okay, so that's what reproducible research, that's where we start. is this idea of computational reproducibility. Now, the idea is really that scientific results should be documented so their deduction is fully transparent. For science to be open and for us to actually have results which are trustworthy, we need the methods, the data set, and the code used all to be publicly available. Otherwise, you are asking people to trust you. And you may be a very trustworthy person. I don't know you. But even if you are a very trustworthy person, there's no reason that someone who doesn't know you should have to trust you. They should be able to check your work. There are significant portions of the scientific literature that are functionally useless because the work cannot be checked, and therefore what was done cannot be understood, and therefore the results are wasted. Now, some necessary components for this to hold. For a project to be computationally reproducible, all of the data and the files should be clearly separated, labeled, and documented. All of the operations should be automated as much as practical, avoiding manual intervention. You know what this means, folks? Excel is verboten. You are not allowed to use Excel anymore. I know it's convenient. I know it's handy. But if you use Excel, none of the actions you take are reproducible. You grab a cell and move it around? I don't know that. You rearrange two columns? I don't know that. You go in and subtly massage some of your numbers? I don't know that. Your results cannot be trusted if Excel is a part of your pipeline. You cannot trust results that have gone through Excel. Something like 50 to 60% of the historic genomics papers published in journals like Nature and Science are broken and not trusted because scientists opened the genomics outputs from their samplers in Excel, and Excel likes to take things and convert them into dates. And so significant portions of the loci information from observations from classical papers were converted into date-time objects and therefore are useless, and all of the coincidence detections and so on would not work on those. You can't open files in Excel and expect your project to be computationally reproducible. You have to train yourself out of this habit. The workflow. So this is what in the bioinformatics literature we call a pipeline. The pipeline, or the workflow, it's a sequence of steps, scripts, combined so that when a script runs, it produces an intermediate output, and then that intermediate output is read in by the next script, and it continues. What this allows you to do is theoretically run that set of scripts and rebuild your entire data analysis from raw data to polished, cleaned, organized, outlier removed data, to initial models, to final models, to diagnostics, to plots that go in the paper. All of that, one press of a button. You can't do that, it's not fully computationally reproducible. And that's what we want. You need to use version control. You have to be able to tell when the files were saved, how they were saved, who they were saved by, where they were saved, when they were saved, and why they were saved. You have to be able to step back in time and see the changes that were made. Otherwise, you could send me a zipped up directory which contains your nominal project, except all of the files are whatever you last left in that, not the version that generated the results that went into the paper that I'm asking you about. This workflow should include the actual data acquisition. Now, this is not always possible. Sometimes you're literally out in a lake doing something, but you're gathering in data in some way. All of the raw data products, the things that are produced by your instruments, by your observations, by your experiments, all of that should be recorded carefully and then stored and never, ever edited again. What you do instead is you data process. You take those entries and you do whatever manipulation and filtering you need to do to clean them. You do that, but you save the first version and the manipulated version so that if I ever question your ethics or your technique or your methodology, you are able to show what it is you did to take the raw data from that particular instrument and turn it into something suitable for scientific analysis. All of your data analysis should also be in this workflow. The computation of all of the statistics you use, the figures you generated, all of the model fitting, including the interim steps. You need to avoid the garden of forking paths. That's a a name that's given to this style of this error in analysis by Andrew Gelman. It's named after the Borges book, the same thing, The Garden of the Forking Paths. The idea is simply that given a raw data set without pre-registration, without knowing what you're going to do ahead of time and having written it all down, one analyst and another analyst taking the same data set can come to completely different conclusions, because it's all in the process of how you step through, make decisions, change your models, decide what to do, and so on. And so this is called the Garden of Forking Paths, is like a labyrinth. It's not ideal. And what it means is that even though you get to the end result and you have a model and you get a p-value, it doesn't mean as much as you may think it means, because you made a bunch of decisions along the way, and every one of those decisions does change the concept of the test. And there needs to be a linear flow. You really need to resist the urge to modify earlier steps. This is the process known as harking, or hypothesizing after the results are known, where you run through the data, you get the final results, then you come up with a hypothesis that you think explains those results, which is doomed to failure. By which I mean it's doomed to success, but that's a failure of the scientific method. So this is hard to do. Don't get me wrong, it is hard to do. But these last two are really a reason why we encourage pre-registration. Now, if you're interested in this and you get to the end of this workshop and you go, wow, this is really cool, I want to learn more about this, I want to be a better scientist, there's a program called Data Carpentry, which is part of the carpentry world or school, which are workshops that teach scientists basic skills in this sort of thinking. I've run through a couple of them myself. They're amazing. They're very well done. And you can go to their website. They have freely available resources, but they also run workshops all the time that you could attend, usually for a fee. You pay a fee for a couple of days, and that goes to the instructor and the carpentries, and then they're able to run these sorts of things. But if you do this kind of process in your research, and really you all do, where the days of being a stamp collector are well and truly done, biology and ecology and environmental science are more statistics than anything else these days. To do that research properly, you have to know how to do these things. So heal yourself. If you want to be a scientist, apply the scientific method to the process you're doing where you do science and make it better. Now, there's some good references. There's a 3-hour training workshop on our Markdown there. There's the Data Carpentry Initiative. There's the Coursera course on reproducible research. There's a book on our Markdown and using it. There's a curriculum for reproducible science. There's some papers, a special issue in IEEE, and so on. And there's basically anything that Mina does. Dr. Mina Setakaya-Rundle, she's a professor at Duke, and she's one of the world's leading experts in this area. Basically anything she publishes is worth paying attention to if you are interested in the kind of thing. She's primarily interested in how you teach this well. She is a professor of the practice at Duke, but all of her materials and resources are good, and she's an amazing person. So basically just read anything she does. In addition, there is a newer reference. I've given this workshop a few times. This is all stuff that's come out in the last 18 months now. There's Building Reproducible Analytical Pipelines with R, which is a book that you can buy on trees, piece of paper, or it's available for free on the internet. There is also an interesting new thing on computational reproducibility. It's a paper on what the 5 pillars are. There's posts about our environment and Docker. That's stuff that we're going to be talking about in a little bit. Some perspective from a psychologist who's organizing his lab to use reproducible policies, and some good practices. And there's also a course from Johns Hopkins, from Stephanie Hicks. It's just the curriculum and stuff, but you can still look at it, which could take you deeper. So that's what we mean when we say computational reproducibility. All right, now let's get started on some ideas. Back to the slide deck. Let's talk about why this is important. So to ensure our research outputs are robust and to maximize the time, money, blood, sweat, and tears that went into them for our future researchers or for society in general, because that's what science is all about, is the betterment of society through understanding the world around us, it's really, really critical you share the underlying code in the data. This allows for replicability of the results. It's part of computational reproducibility. If this immediately threw up a red flag in your head, or if your immediate response was, no, I will never share my data, I want you to stop and think about that. Why did you feel that way? What is special about your data that you don't think you can share it? And if your answer isn't, it contains private information about human beings, then I really start to question the quality of your research. Because if you can't share your data and allow someone to reproduce your results, I don't know if I trust your results. Because that says to me that you're nervous about the methodologies that went into the manipulation and analysis of that data. Now, that may not be true, but by default, that's my approach to things. If you're not willing to share your data and your code pipeline that generated your results, I don't trust them. Because there's been way too many cases of genuine errors, not maliciousness, but errors by scientists, because they make mistakes. And without the data, without the code, I can't check your work. I can read your paper, but I don't trust that you didn't make a mistake. I make mistakes all the time. And so that replicability, this idea that all of the results should be computationally reproducible, that's incredibly important. So here's some quotes, just some things. I first came across a lot of these ideas in 2016 when I was at a couple of sessions of the Joint Statistical Meetings in Chicago. And this was the first one that made me sit up and go, whoa, yeah, okay. So this is a quote, and it was from a talk by a man named Carl Broman. He's a professor at the University of Wisconsin-Madison. He's a statistician who primarily works on genomics. And he threw this up as has this ever happened to you? And it was like a screenshot of this email. And it said, Carl, this is very interesting. But you used an old version of the data with 143 samples instead of 226. I'm really sorry you did all that work on the incomplete data set. Bruce. Now, I want you to cast your mind into the role of Carl here and imagine you've just done a statistical consulting project and you have analyzed a full data set. You've gone through all the work. You've generated the results. You got the figures. You're basically ready to publish. And your co-author's like, whoops, I gave you the version of the data from 6 months ago. Really sorry about that. You're super efficient. You banged through it before I realized there's a whole bunch more observations. Now what? Now, did your stomach sink there? Did you go, ooh, yeah. How many hours did I just lose? Or did you go, probably no problem? This is the difference between whether your results are computationally reproducible or not. If you can plug in an updated version of the raw data set and rerun all of your analyses, and all you have to do is check the results as they come to see if any of the conclusions changed versus not, that's the difference between computational reproducibility and not. What happens if, say, reviewers come back for a paper, and if you're in the stats literature, reviews can take 10 months. I had one paper that was 11 and a half months between submission and reviews. I had graduated and moved on before the reviews came back. We never did publish that paper because it came back so late that everybody had moved on. What if they come back, but they're like, oh, wait, I don't really know what's going on with this one model. Can you check this one model? And when you go to do so and you go to run it, nothing matches. None of the outputs, none of the figures. You rerun it and nothing matches. It doesn't even seem to be the same results that you published in the paper. What just happened? Let's say you send a script with some data over to a collaborator. You're like, here, I got to figure this out. Model's running great. Here, run it for yourself and see. And they're like, it doesn't work in my computer. That could be your collaborator who you used to like, or it could be your PhD supervisor who doesn't really use the same programs, code, packages, whatever that you do. And you're just like, oh dear. And now all of a sudden you're worrying about tech support instead of focusing on the science. Or have you ever done this? Hey, I'm done my document. Final.doc. Nope. Final revision 2.doc. Final revision 6 comments. Final revision 8 comments, corrections. And at the end, you're like, why did I go to grad school? I once wrote a paper, a published paper. We did finish it with 7 or 8 co-authors, I forget. And because those co-authors didn't know how to use any kind of good methods, I had to write the paper in Word, which I mostly swear off doing. It just makes me miserable, but I wrote the paper in Word. And then the PI for the project sent the paper out to all 8 collaborators, and each of them turned on track changes, made edits, and sent it back. I then had 8 different versions of the edited paper that I had to somehow synchronize. That was the worst 2 days of my postdoc. It was miserable. Ever happened to you? If not, you just haven't collaborated with enough people. So why is reproducible encoding important? Well, for one, your personal sanity. You don't want any of those previous things to happen. You want to be able to be like, oh yeah, I got this. Let me press some buttons. The scientific endeavor. At the end of the day, that's what it's all about, isn't it? We're all here to discover truths about the universe. We care about science. Having things just work. It's very, very relieving when things just work. Avoiding the embarrassment of sending something over to a collaborator and then it doesn't work because you didn't design it to be computationally reproducible and it only runs under a certain thing in a certain computer at a certain time. If the moon is right and the black cat walks across the road, you want it to be generally robust and to work on other people's computers. Here's some other notes. This is from Jenny Bryan. She's a former associate professor of statistics at the University of British Columbia. She's now a senior staff scientist at Rstudio. File organization and naming is a mighty weapon against chaos. How you name your files and how you organize your files is very important. That quote from Mark Holder about collaborating with yourself. Unfortunately, you from 2 months ago is really bad at answering email. Hadley Wickham, probably the world's most famous or preeminent R scientist. He develops packages for the R environment. He's on a lot of advisory boards. He's the senior scientist or the chief scientist at Rstudio. Even he is saying, dear past Hadley, please comment your code better. Love, present Hadley. Even he, who does this for a living, still goes back to his code and is like, what was I thinking? And Keith Baggerly is maybe the grandfather of this whole thing, especially in the statistics community. The most important tool for reproducible research is the mindset when starting that the end product be reproducible. So some basic principles. This comes from that talk by Carl at JSM. Number one, slow down and document everything. Step two, try to think about future you and have some sympathy for yourself. And step three, have a system. Now, what that system is very, very general. You can have almost any system, but you need a system and you need to follow it religiously. Because then, when you go to look at it later, you'll be like, yep, I know where it is. I stored it in the usual spot because I have a system. So some tips for getting started. This is overwhelming. There's so much to do. And if you haven't grown up in this field, if you haven't been doing this for years, if you don't have a lot of experience writing code and doing scripts and stuff, this can be very overwhelming. Number one, just take your current project, whatever it is, and force yourself to organize it. Put everything in coherent spots. Think about what future you in a year is going to be thinking about and try and organize that project so you know that it will be in a coherent setup for future you. Or use Git to store some materials. More on this soon. This is what we're going to be looking at today. Create slides for the next thing you have to do. Maybe that's a conference talk or a brown bag lunch or a lab meeting you're going to have with your lab group and your PI. Make it in our Markdown or Quarto or an equivalent framework so that it is something that you can version control and store. And then every time you do a subsequent project, try to add just one thing, just one more thing, and grow that way. Finally, or not finally, but next, think of all of the outputs of everything you do as being code. This can include teaching. If you prepare slides, those slides can be considered as code. And that means when you make changes, you can track them. Here's the personal example. After I kind of was inspired by all this, I converted all of the slides for all of my big classes to R Markdown. And so then I knit them as part of a project. And the course itself is a Git repository, so this has a large number of advantages. Number one, all my slides are publicly available. You want to rip them off? Go ahead. I don't care. That's why they're licensed to CC BY. Just give me attribution and say where you got it and have at it. It's very, very easy to update the course website. Well, I do have to use Blackboard because that's what we use here at Trent. I can just reknit a file, commit the repo, push it up. We'll learn more about that in a minute. And the website's updated. I never lose my old slides. They're all synchronized between my computer. And, I have copies of like 4 different computers across my personal computer at home, my office computer here, my laptop, and then a cloud option. But I also have them on GitHub, which means I always know where to go to look for them. And then it's trivial. because they're actually a web page to cross-link between lecture to lecture, or to steal a lecture that I've previously looked at and just reuse some material or a nice example I came up with. It's easy to reuse my own work. And I do a lot of teaching. I mean, primarily that's my job 8 months of the year is to teach. And so that means I'm constantly using these science skills even when I'm teaching, which helps me when I go to do science again. They're there, they're fresh, I haven't forgotten how to use them. So the lectures are code. Depending on how computational your world is, this may not even sink in. What is code exactly? It's text, all text. If you can open it up in Windows Notepad, it's text. That means I can edit it on any computer. Don't underestimate this. Looking around the room, there's some people with Mac computers, there's some people with Windows computers. If you create a Keynotes presentation and you send it to a Windows user or a Linux user, they can't open it. If you set up a PPTX in the latest version of PowerPoint and you send it to anybody who doesn't have that latest version, they can't open it. But if I send you a markdown file, which is a text file, you can open it on any computer that's existed for the last 30 years. You may not be able to render it, but you can open it and edit it, and that's important. It's rendered in some way. Now for PPTX and all of that stuff, it actually stores it all as code in the back end. It's actually a whack load of JSON. And then from that, it renders the presentation as you see it on the screen, but that can be true for almost anything. And because it's code and it's just a series of ASCII or UTF characters, it is trivially versionable. It's very easy to track changes in something like that. Compare this to PPTX. It really doesn't work unless you have PowerPoint. You can open an old PPT in like OpenOffice, but even then you need a program that can open the WYSIWYG kind of JSON, turn it into something that makes sense and allow you to edit it. Whereas my markdown files can be opened on any computer anywhere in the simplest programs you can imagine. So some tools that you might want to consider using. First is a package called Use This. It is a package for R developed by the folks at Rstudio. It has support for a bunch of common things like setting up a Git identity or a Git repository, pushing and pulling to Git, and so on. It's just a general purpose package that has lots and lots of practical tools in it. You can set up your Git credentials. You can create a project from a repository, open and edit your R configuration files, interact with a repo to branch and commit. We'll talk about what those words even mean in the coming material. Or work with projects, packages, and so on. A second one, and this is really important if you want your work to be portable, is the here package. The goal of the here package is just to enable easy file referencing. Set working directory. How many of you have ever written an R script and the top two lines are rm list equals ls followed by set working directory to c:/my/computer/is/the best? Too much in there, but you see what I mean. How many of you ever done that? There's a famous slide somewhere from Jenny Bryan, that woman I mentioned a minute ago, which just says if she sees that rm list equals ls in your script, she will come to your house and burn your computer. It is a very bad habit to get into because that line nukes the local environment of anybody who runs it. So if somebody goes to run it not expecting that, they've just lost whatever was local forever. That's a bad habit to get into. And the set working directory only works on your computer. I can guarantee that. Unless you set up an identical environment across multiple computers, when you go to run a set working directory that has an absolute file reference path, it doesn't work. Here is a package designed to allow you to do relative file referencing so that if you send your project to someone on a Mac, say, but you're on Windows, or on Linux, you're on Mac, it will still run. It's important to get your head around how the ways that happen and so on, but this is important. This is a nice little illustration. If you haven't come across Alison Horst, she's a scientist. She used to work at the Bren School for the Environment at UC Santa Barbara, UCSB. She's now an independent scientist. She took a job working for somebody, but she's also a really talented artist, and she makes these little cartoons, and they're kind of amazing. And so this is what the point of the here package is. And so you have a little exploring little dude, and over here is not here. And there's things like non-portable code and tilde/mm/nope.csv, set working directory, haha/good/luck, and oh no, and I am your nightmare, and there's like little monsters. And over here with sunshine and rainbows and like everything's happy and bluebirds. It's like, just do here. It's right here. Seriously, it's just here. Go. So if you haven't checked her out, she has all these figures on GitHub and lots of cool stuff, and she's on Twitter. She's a really fun person. I invited her to give a presentation, or rather paper. I think I did recently. I met her. She's a lot of fun, and her artistry skills are amazing. I like to use them as little snippets in my slides. Now, the key with here is that anything you do manually, you can do this, but you really shouldn't. Machine portability is hard, and set working directory and stuff do not work when you're transferring things across different computational environments. This is especially bad when going from, say, Windows to Mac or Linux. And remember, almost all high-performance computing is Linux. So if you ever get to the point where you need to start running stuff on HPCs like Alliance Canada, which used to be Compute Canada, or even just on a more powerful server that your PI has, it's going to be Linux. And so your code needs to be able to transfer because it needs to not be Windows specific or Mac specific. Here forces you to think about that, which sets you up for success in the future. Now, in the next session, we're going to dive into a version of what we've been calling version control, and it uses the Git version control language, which was developed by Linus Torvalds, the same Linus Torvalds that is the chief maintainer and original creator of the Linux kernel, which is the most wildly successful open source project in human history. And he invented Git specifically to track the changes in the Linux kernel because he wasn't happy with Subversion, which is what they had been using before. So we're going to introduce the concepts, get you started, get you set up, and then we will proceed to test. All right, as promised, let's get back to this in version control concepts and learn a little bit about version control and how it works. Again, this quote. I love this quote. I think it really resonates with people, and I want you to just, if you go away from this workshop, and this is the only thing you remember, maybe you will use it to have some compassion and patience with yourself. So what is version control? Well, we've already seen that picture, that final.doc, but version control is the process of keeping a record of changes to documents, when they were made, who they were made, throughout the entire history from the moment the file is created until the present. It also provides the means to view the earlier versions and to revert the changes. So this is more than just tracked changes. If you track changes in Word, once you accept the tracked changes, there's no way to go back. But in version control, we accept the changes all the time, but we have an annotated version that lets us step back in time to be able to see changes that were made. To version control a project, usually two things: a version control system and a repository hosting service. Now, the latter is not strictly required. You can just do version control on your local computer, but that loses the best part of it, which is that it's also a built-in backup system. And if you synchronize your version control to a second computer, you then have a backup if anything goes horribly wrong and someone breaks into your house with a baseball bat and beats your computer to death. So why should I use it? Well, without a deliberate, conscious effort when you're tracking changes, projects tend to become messy, like this Charlie Day meme where he's conspiracy theorying it up, right? But everything is just like a mishmash, and you don't know what happened when and where and how and who. So why should you use it? Well, it also facilitates collaboration. It allows you to share your edits with other people. It allows you to resolve conflicting edits. It allows for democratic communication and peer review. It allows for project management. It's generally a very useful thing because it opens the door to things that are good. Now, typically, when we put a data analysis project under version control, we will create two copies. There will be one that is local, say on your laptop, and there is one that is somewhere else, like say on GitHub, which is it's a pretty common place. It's very much the standard for open source code and for referencing things. And there's a nice student version that allows you to sign up as a student and get some benefits, or it's like $7 a month to have private repositories and the basic features. And I've been paying $7 a month for it for close to a decade now. It was recently, in the last couple of years, purchased by Microsoft. So it is owned by an extremely large, extremely stable software company who understand what it is and how it works, and seem, so far at least, to have no interest in breaking what is one of the most powerful tools we have in the modern world for software development. So how does it work? Well, the history itself and all of the files are synchronized. So what we have here is the remote repository on the right-hand side has two steps: the initial creation of the README and the local pointed head where it says that the analysis draft has been added, with two files, the README and an analysis IPYNB, which is an IPython notebook. These two files are there and they're current versions. Now, the local version is at the same stage of tracking, but in the working directory here, we have a third file called notes.txt, and the notes.txt is not being tracked. So the neat thing about version control is you don't have to track everything. You can have a file in your directory which is enormous or is just like rough work or something, and you don't track that. You don't care if that disappears. Like, again, my analogy, I break into your house with a baseball bat and beat your computer to death in front of you. If you lose that file, you don't care. And so it's not tracked. Now, what happens when you make a change? Well, we control the local changes and we synchronize the remote and vice versa. If we have multiple people using the thing, then we can all do that back and forth without needing to go between our computers. Because one of the most annoying things about computers is that even now, we've been using personal computers for the better part of 40 years. It's still really hard to transfer files between computers, to the point that you do things like emailing it to yourself. Now stop and think about that. You use the email protocol and an email client to attach a file to an email, which why we ever allowed that in the first place is a mystery, because the email protocol wasn't designed for files. Send it through the internet. It bounces off 19 servers, 3 routers, and 27 switches, and it makes its way to the email, after which you go to the other computer and you check your email, at which point it sends you that email that you just sent back down through a different route, so you can download that file from the email system onto that other computer. If it wasn't so common, we'd think it was insane. So when it comes to code and stuff like that, we don't want to do that. We're going to just track it by synchronizing these repositories directly over the internet with a remote GitHub. So let's say I go in and I start typing, okay? I'm making some changes to the local file. So in my local computer, I'm on my laptop, and I have made some changes to these local files. All 3 of them have been changed and saved. Nothing in the repository system, which is the next layer, has changed at all. What I have to do is I have to take those local 3 changes and I have to tell the computer which files should be added to the tracking. In other words, I want to track those changes. What I do is I move them, I tag them into the staging area. And so I say, hey, Git, I want to take the changes to the README and the changes to the IPython notebook, and I want to put them in the staging area. And now at this point, they're still not saved. I've just told Git that the changes I've made are probably something I want to save. Once they're added, I then form a commit. So it's a 2-step process. Choose the files you want to save, and then formally sync it in stone. And then I commit, and I type out a big long message, and I say, okay, I've made these changes for this reason. Here we go. This is an informative message, and I commit. At that point, my local repository now has a new benchmark or a new reference point where I can take those files and I can look at them at that moment in time, because it's now saved for all time, or I can step back to the previous version. Now, this silly looking made up thing on the top, that's a hash. And hashes are really important. They basically tell you a binary reference for what the files as a whole are like. You may have used hashes before when you were dealing with downloading really big files, because they have these things called SHA hashes, where if you download a really big file, after you've downloaded it, you can hash the file. And if it's different than the version on the website, which is like, this is what the hash should look like, you know something corrupted in the process of downloading it. So it's a way of verifying the binary matching of some data or some files. Okay, so you've done that. Now, that's local. The remote is still at the last moment in time that you synchronized it. And so what you have to then do is take the current version of the repository, which means really this pointer here and this latest version, and we push it up to GitHub. At which point that repository updates, all the new changes are rolled forward, the latest save point, like a video game, is established, and everything is now synchronous. Now, if I say that to take it from local to remote is a push, then what would you think from remote to local is? Well, that's a pull. So now let's say I'm working with a collaborator, and they may be making changes as well. And so they grabbed the latest version of the repository, which was this pointer at this 6FD6ACB reference. They pulled it to their local computer. They typed, and they made some changes. They added those changes to the staging area. They committed them and said, more changes, ! And pushed it up to GitHub. Now those only exist remotely, not locally. And so when you go to use the project, you have to get in this habit. The first thing we do is we complete a pull, because that will make sure that we are synchronizing our local machine with our remote machine at the moment before we start our work. Now, you don't have to do this all the time, obviously, especially if it's just you, but it's the kind of thing you want to do just to be sure before you start working on something, because if somebody made a change and then you don't notice that change, you get desynced. And once the repositories are desynced, you run into all kinds of problems, including one very major one that we'll talk about in the second half of this workshop. Now, when you're collaborating, if different files are changed, or even different lines on the same file are changed, Git just handles this. It's like, yeah, totally. I understand what's happening. It's all good. There's no problem. I got this. However, when two collaborators change the same line, Git's like, I can't handle this. I just can't even. Human, figure it out. And so when this happens, the human task is to find the spot where what's called a merge conflict happened, figure out which version you want to save the file after having done so, add it to the staging area, commit, and synchronize the repositories. It's the most scary thing you typically do when you are working on this sort of stuff, until you get to more advanced topics with branches and stuff, which we won't talk about today. So this GIF comes from The Big Bang Theory, which was overall quite a horrific show. Not actually a very good show. It's a Chuck Lorre show, which is exactly what you expect. But it does have some funny moments, and Sheldon is an interesting character. Jim Parsons did a good job. So this is him just like giving up, throwing all the paper in the air, and turning around to stomp away. So this is a good spot to stop. So we're going to have a coffee break now. And then when we come back, we're going to take a look at merge conflicts, how they work, and then we're going to do a practical example where we're all going to try and actually do this. So we'll stop the first video for now.